Okay, so let's give it another try. Basically, where did we leave last time? So we left where we thought about like strengthening, so different degrees of strength that an entanglement state can have, or an entangled system can have, and we're still just at 2 qubits, okay? Now, playing with this idea, I also came across another setup where, I think I shared this in Twitter, where instead of changing the phase or the relative phase of the one of the computational branches, if you, I think it was like, if the relative phases of each computational branch are like opposite, then you're having like the maximum entangled state. If not, like you are getting like different gradients, or different, like not gradients, different degrees of strength. If you play with the probability of the control qubit before applying the entangle gate, you also get a similar effect. So if you, let's stick to the state that we had before in the other sessions as well. So we had like a qubit in the plus state, another qubit in the plus state, both target and control. And the entangling gate was a control set, right? So what this does is it creates 2 computational branches, where the target qubit is on one branch, it stays in the plus state, in another branch it stays in the minus state, and that's maximally entangled. Now, if we play with the probabilities, or if the control qubit is not in the plus state, and we vary the probabilities of observing 0 and 1, right? So the probabilities that will be then associated to each computational branch, you get the same computational branch, obviously, because the target operation didn't change, but you get different degrees of strengths when you take a look at the at least at the block spheres, right? Now, I don't know if this is anyhow useful. What could this be useful for, right? You have, because at the end of the day, what this means is that you have a state where, like, you have a system with two computational branches where one of them has like a higher probability than the other associated to it, which I don't really know yet what it means, or whether this is useful anyhow computationally speaking, or like, can you do something with it? Because it doesn't seem like the branches can interfere, and so I don't know if this is something that tells you about the strength of entanglement in the system. I don't know. So, but it's like, if you, for example, instead of being in the plus state, you are like half the way to the plus state, then you're like, your computational branches look the same, but it's not like the two qubits, they are not like maximally entangled. That's another way to see it. Like, what I like about this is the fact that you're not changing the computational branches, right? So you're basically, what you basically have is, you have you kind of have I mean, how would you say this? So you have the same computational branches. They have different probabilities associated to it, but you don't. I don't know whether this is taking me anywhere useful, to be honest. I mean, you have the same type of computational branches. That's kind of what's useful. Now, why would you want to play with different strengths, right? If you can't think of the branches being somewhat like, or interfering somewhat like, because the computational branches kind of concept makes sense, as in like that's the parallelism that people talk about to some extent, right? Okay, it's not, because people talk about these in terms of superpositions, not necessarily entanglement. Now, things, I don't know, I'm a bit stuck. I'm really feeling stuck here. Like, what am I trying to understand? So I'm trying to understand, I'm trying to characterize entanglement somehow. I also kind of had the thought that I could, like, this is a bit of a path towards how to create entanglement without really referring to a circuit, right? Like, you can think of a programming language and where you say, hey, I want to entangle 2 qubits. Okay, but I'm already talking about qubits, but like, okay, I want to entangle two variables. So I'm gonna define this entanglement object or resource. I'm gonna associate the 2 variables to it. So I'm gonna say something like, E, which is a new variable of type entanglement, equals new entanglement, and then I would give it like the 2 qubits that I want to entangle as resources, and I would give it like a desired strength, and I would give it maybe something that would specify the computational branch, like the type of computational branch that I want to create. But why would that make sense at all? What do I do with this later? Okay, then you have some sort of a variable that's of type entanglement that you can do something with. But it still feels like I'm kind of locked into the classical paradigm of like functional programming or something, where you have objects and you do things with them. But I don't really know where this is taking me, to be honest. I mean, I've taken a look at it from the control side of things, from the target side of things, and we're just thinking about 2 qubits. We're thinking about the strength of entanglement as it being a property that is maybe somewhat useful. I've definitely heard of this being useful in terms of the stronger the entanglement, the more resilient it is to noise, or something like this. But I want to have something be more functional attached to it in terms of benefit. Like, for example, that with weaker entanglement, but it doesn't make sense even to think about strong or weak in those terms, at least. I like to think about the probability of each computational branch existing. Maybe entanglement per se, it's just a concept that... What if we think about 3 qubits? Maybe that will help us and block us a little bit. Because you can, like, how can you entangle 3 qubits, right? Like, you can... Here you've got more possibilities, because with 2 qubits you have, like, either you entangle one with the other or the other way around. I suspect that most of the stuff you can do here is just equivalent, so you basically have one setup. So you have one of the qubits as control, another one as target, and then it doesn't matter which one is which. You just have one configuration possible. Now with 3 qubits it's a bit different, right? Because you can have basically now, you can think of, and I think I don't care which qubit is which. I just know that I have 3 resources, so I can think of basically entangling 2 as in, and so with such a configuration you probably have maybe, you can kind of control, so you can do entanglement, but like controlling 2 operations, 2 of the qubits with another one. So in which case, I guess you'll have 4 different computational branches, right? And I think no matter how you look at it, like even if you chain the controls and you kind of entangle one qubit with another, and that one with the other one, you also have 4 branches. It's just they'll have a different shape, right? Like there'll be some of them nested in this case, I guess, and the other way they won't just be nested. Now, so you've got nested computational branches. That's another concept in here that might be worth exploring. Other than that, it doesn't seem to be especially more exciting than the 2-qubit case, right? Like then you're gonna have different strengths associated to these, I guess. This I can play with in Quirk, I guess, but maybe this nested concept, like, which kind of happens the same if you think about like the swap implementation with 3 CNOTs, whereas like you have first the CNOT gate between between one qubit and another, and then you have another CNOT gate that kind of works the other way around, and that sort of nests computational branches in as well, because it's kind of using the control, like the previous target as control for the next entangling operation. And maybe this nesting is crucial to the interference, because to the interference between branches, maybe this nesting is what's kind of crucial there. I don't know. But so there's this nestedness to it. And I think the more qubits you add, it just gets, it doesn't get more interesting, right? Just have fancier nesting patterns that you can do probably. But I wonder whether you can do something like recursive computational branches where, that would be what the 2 CNOTs like upside down would do, right? Like in the first 2 operations of the CNOT decomposition of a swap gate. Would it? No, that's not recursive. Can you do something like this? Could you think of like recursive branches? Sort of a branch that like it kind of calls itself. No, it's not about calling, to be honest. I don't know. Can you do recursive computational branches? That would be an interesting concept. Something interesting to take a look at. So you've got the nestedness in there with multi-qubit entanglement, but it's still, it doesn't seem to take me anywhere. So I have to think a little bit about this more. So I'm really not sure. Actually, I just came up with another idea. Like, as we have, as you can have other controls than just like the control on the z-axis. Like, for example, you can have a control on the plus or the minus, so on the x-axis, for example. But just like sandwiching a normal control with a Hadamard, like, is it possible to create even more branches? Like, with 2 qubits, right? Like, if you just apply a control Z, for example, to the plus system that we talked about, then you have like 2 computational branches. But if after doing this you apply a sort of a control on another axis, an operation that's controlled on another axis, like, would these create 4 branches? It's an interesting question. It's an interesting question, actually. I don't know. That would be interesting, right? Because it would be interesting to think about like whether this is the right thinking framework. Like, because you think about entanglement as a static resource, right? Like something you create and it stays there. So you kind of have these 2 computational branches after applying an entangling gate, and then you kind of. Or at least I think like they are just there sitting, and I can operate on them and then do stuff. And but still, how do I reconciliate the, maybe before adventuring a bit too deep into the sort of more than 2 computational branches thing? Like, I could think of like, what is the right mental model for operating with computational branches? Like, are those 2 things that just stay like that isolated? Like, can you interfere them somehow? Because that would be the point of, I think that would be quite useful, right? Like, that would be a bit more of a way to think, okay, I can create like different threads of computation, and then eventually you could just escalate, like, you could just like level these up, right, at the register level. So you have like registers that are entangled with other registers, and so you have registers that can kind of hold like, so you actually have registers that like have then different computational branches. But I don't know where this is going. It's a way to think about entanglement for sure. But I don't know if it's probably not the only one either. But okay, so we touched computational branches. Maybe there's some nesting you can do there. Maybe there's something you can do with multiple axis controls. But maybe I should just go on and like maybe get my hands on maybe just a very basic concept and try like just 2 qubits and then do the computational branches and try to do something useful with it. Maybe that'll be the next step, rather than just like keep thinking about it like out loud, because I think it's not going anywhere else, to be honest. It's really I don't know if it's really going anywhere else.